It should come as no surprise that just like the position vector could be described in component form, that leads to the velocity vector being described in component form, 3 dimensions, that the acceleration vector can be described in the same way. And so we have acceleration. I'll use a new color for acceleration. Let's go with, I usually go with pink for acceleration. We'll do that. So the average acceleration is equal to the velocity vector 2 minus velocity vector 1, right? So the velocity at some position and velocity at some other position divided by the time difference, t2 minus t1. And that would be delta v as a velocity vector divided by delta t. And so this results in a vector, average velocity. And just the same, you can also express instantaneous acceleration. And I'll just write a instead of specifying instantaneous, because pretty much from here on out, if I just write the vector a or the vector v, we're talking about instantaneous, is the limit as delta t goes to 0 of delta v divided by delta t. And that can be written in component form, the vx dt I hat plus dy, dvy. So the component of velocity in the y direction, dt j hat, plus dvz, component of velocity in the z direction, k hat. And that can further be written d squared x dt I hat d squared y dt j hat plus d squared z dt k hat. So dvx is just dx dt, dvy is dy dt, and dvz is dz dt. And likewise, a x would be dvx dt, or d squared x dt, and so on. This, what comes out of this is a very interesting result, and it's not intuitive to most students, mostly because of what we refer to as acceleration in physics is different from the colloquial understanding of acceleration. So you think of acceleration as simply speeding up or slowing down, but acceleration is any change in velocity. Any change in velocity. That could be magnitude or direction. Yeah? So magnitude or direction could change and you have an acceleration. So that means you could be traveling at a constant speed and yet there is still an acceleration if you simply take a curved path. So if that's your path and you're traveling at constant speed, then you are accelerating. How can that be so? Well, we'll explore the forces that are coming into play, and it might solidify it later, but for now, suffice it to say that you can get a nice intuitive understanding of why. So let's see if I do a path in this kind of color I was using for position before. If your path is like this, then your velocity, which I believe I used What did I use? I don't remember. Oh yes, this kind of reddish color. Your velocity is tangent at all points, right? And your acceleration, in order to produce this curved path, is perpendicular to the curve, like this. So when you're riding in a car, how do you know that the car is accelerating or decelerating? If you had your eyes closed and you're sitting in a passenger seat of a car and somebody was driving, how would you know that the car accelerated? Well, you'd be thrown back in your seat a little bit. And how would you know that the car slowed down? We don't like to use the word decelerated because you can have negative acceleration, and that's really what it is, instead of decelerate. But how do you know the car slowed down, thereby experiencing an acceleration in the negative direction? Well, your body is thrown forward, right? So what happens if the car takes a sharp left turn? If the car takes a sharp left turn, which way is your body thrown, or is it not at all? Because this indication that we have of our body is thrown forward or backwards is our indication that there is acceleration. So if the car turns left, your body is thrown right. So there must be an acceleration, right? Or if the car turns right, your body is thrown left. And so in the same way as accelerating forwards and backwards, we have this acceleration left and right as the car turns. So we'll explore that in greater detail in the next lecture, lecture 4 and beyond. But for now, let that be an intuitive understanding. Let that suffice for an intuitive understanding of that there is acceleration with constant velocity on a curved path, as long as the path is curved. So, in summary of that point, anytime there is a change in velocity vector in any way, whether that's speed or direction or both, you have an acceleration. So, because of this, it is useful to look at the acceleration, that component that is perpendicular and then parallel to your velocity vector, because they tell you two different pieces of information. If your acceleration parallel to your velocity is non-zero, then you are either accelerating or decelerating. Right? So let me draw this this path out again. Let's see. Let's go with this position. This is your position, curved path. Your velocity, let's say at this point here, velocity is of course tangent to the path, and your acceleration, if you were maintaining a perfectly constant velocity, your acceleration, like I described before, this is the same picture that I drew before, your acceleration is as such. But your acceleration doesn't have to be that. You could be accelerating as well as turning, right? So let's say that we are increasing our speed as we go on this path. So our velocity at this point is such, but our velocity back here was smaller. And our velocity here is larger, right? The length of the arrow corresponds to the magnitude of the vector. So we're increasing our speed as we go on this curved path. What does the acceleration look like in order to produce this motion? Well, we have some component of acceleration this way to produce the curved path. That must be present. If there was no acceleration this way, then our path would continue along in a straight line. And so this is perpendicular acceleration, but we're also increasing our speed, so there must be acceleration parallel as well, some component of parallel acceleration. Let me unbury that. Right? Well, they're components. And so if you have both going on, and these are each components, right, at right angles to each other, then the true velocity vector is described by this vector there. This is the acceleration. So this is the acceleration vector, and it can be broken up into parallel component and perpendicular component. The parallel component tells you if the particle is speeding up or slowing down, and the perpendicular component tells you if the path is curving to the right or to the left, if the direction is changing, in other words. What if we had a particle that was going on this curved path, and it was slowing down? So velocity vector here, very fast. Velocity vector, very large. Here, slower. And here, much slower. Yeah? So it's slowing down as you go on this curved path. So what must the acceleration vector look like to produce this motion? Let's talk about right here. So the perpendicular component must be this way to be curving the path. So there's some perpendicular component to acceleration that way. But now we're slowing down. So the acceleration is going to be in the opposite direction from our velocity. So instead of contributing to larger and larger velocity as we go on, right, the difference in velocity in some per unit time is not increasing, it's decreasing, then the parallel component of our acceleration must be in the reverse direction of the velocity. So it's taking away some of the velocity as you go. And so the full acceleration vector, made up as a combination of these two components, is such. So it's just a little bit behind the perpendicular to the velocity vector. All right. Next, we will talk about projectile motion, which brings all of this into play in 2 dimensions, like I mentioned earlier. And then we'll do some problems related to that as well.